So I'm Lita. So I'm on behalf of my postdoc, Dr. Zhang and Dr. Wu, to talk on this topic. I'm going to summarize what we did for LiDAR localization for the past 5 years, and now we'll come to a point that we determined that the integrity monitoring is the holy grail. So this is the way to go. This is the thing have to be done in the next 5 to 10 years, I suppose. So we're gonna talk about that. So a bit of advertisement of myself. So I'm come from Taiwan. So I do my bachelor and PhD also in AA in National Cheng Kung University. So my PhD supervisor was graduated from GPS Lab, Shaoxin. And then I went to UCL, worked with Paul groups for 1 year as a visiting researcher. Then I joined Tokyo Marine University to work on RDK and stuff in urban Kenya. Then finally, I come to Tokyo University as postdoc to work on autonomous driving and how GNSS is important for that. Then I joined independently to Hong Kong Polytechnic University, working there for 6 years. So I'm very lucky. After 6 years, I can have my first sabbatical to work with Frank at Google. So this is who I am. So very nice to meet you all. Yes. So I want to talk about what I like and why I work on this so much and why I can start talking about it. I come from Taiwan. You know, this is a Taiwan's building. This is a Taiwan's building, Taipei 101. It's a huge urban city. And I was working in Tokyo for 3 years. There's a crazy urban as well. I was living in Hong Kong, which is even more crazier. So whenever I put on my phone, so Frank, which work harder, put on my phone, I still cannot find myself in many of the environment, like urban Kenyas and indoors. We're still working on that. We are getting better, but we're still getting there. And I'm looking at, as a researcher, as a navigation researcher, we have so many different technology. We have different sensors, we have 3D models, we have digital twins, we have connectivity. I'm looking at all this technology to leverage into 2 applications. Is it smart devices or is autonomous driving? So a large, I would say 70% of my work is working on the smartphones, smart devices, using local sensors, GPS, IMU, Wi-Fi, UWB, 3D models, map, and computation really low, but we aiming for 1 to 3 meters, and integrity is not required. While a very different game, autonomous driving systems, autonomous systems. You need a very good sensor, you have a very good geodetic antenna, RDK, very good IMU, technical grade IMU, you have a LiDAR, expensive cameras, you have HD map, which is big business there. You have very strong computational power, and you require 10 centimeter, and integrity is required. So that's a very different game. Today, my talk is going to talk about LiDAR integrity. That's all my talk today, okay? Right. So this is the outline. So what is LiDAR and how it works for navigations? This at first I talk about principle. Then I talk about LiDAR's length, what is the methodology and challenges. Then I come to the point of LiDAR matching, which is very important. This is the key for autonomous driving to do localization. I'm going to talk how to translate a classical GPS integrity monitoring method to LiDAR matching and what's the challenge we have. And then it's the conclusion and future work. All right. Right, so a principle of 3D LiDAR. So I suppose most of us working on GPS here, right? Is it? Should be, right? Yes. So LiDAR is very similar to the Wi-Fi RTT. That you submit a light pulse, and you have the 2-time flight. Then you have the distance between you and the object. Very simple. So basically, depending on the channel you have, we're talking about the paradigm, the more popular one. So you're going to have a different channel, sending out the signals in different elevation angle. In each of the channels, they send out different poles. Okay, each of the channels send out different poles. So that when it's received the reflection, comparing the poles, you know which channel it is. Okay, so when you do some small robotic car, you buy those 2D sensor, 2D LiDAR, then when something comes really close, you cannot know. The LiDAR just don't give you measurement because of that distance shorter than the poles required. So that's what usually happens. So this pose is very important. So it may you to understand which channel you are looking at. All right. And after you have the different channel, for example, 3260, you have the different elevation angle, 3260, then you have the motor to rotate, okay, oscillator and also to record the rotation 360 degree. So after that, you're going to have a 360 degree and 32 channel like this, okay? This is how you scan. So your measurement in the end is the distance from the sensors to the surroundings, 360 degree. That's what you have, okay? Pretty simple. Then, how LiDAR autometry works? Usually, when I come into a new navigation technology, so I'm looking for sensing, measuring, and measurements. So the sensing is what I just told you. You send the pulse light wave two-way time of flight. Then you got distance, and you have the measurement, which is the point cloud data. And our goal is to get position and orientation, 6 degrees of freedom. So what is the model? So for LiDAR autometry, using the surrounding environment as the model. Okay, that's the model that we have. So if you're looking at this is your current scan, like point cloud data coming in. This is your previous scan, previous epoch of time, previous scan. That previous scan is going to work as the model, comparing with your measurement to give you position estimation. That's how it works. So if you put it into a small MS equation, it's pretty simple. You have the previous epoch scan, P over here, and you have the current scan, P plot over here. So what you're going to do is you're going to do the rotation matrix and translation matrix, going to rotate 60 degrees to make it as a match. Make it as a match. Find an RT rotation matrix, translation matrix, make this function almost 0. Then you get what you want. LiDAR autometry, pretty simple. So after that, you get this so-called transformation matrix, which is including rotation matrix and translation matrix. Then your final product at this particular autometry is transformation matrix from time, body frame of time, epoch t to t-1. This is what we have. By doing this, comparing the two epoch of the point cloud, you can get autometry, translation, rotation between two time. That's why we call it autometry. So what is SLAM? People talk about SLAM so much. It's a very, very hipster word in navigation world. You always do this SLAM is simultaneous localization and mapping. So just talk about odometry part. Where is the mapping part? Okay, for odometry, it estimates the estimation, the transformation between the current and previous scan. That's what we say. You can do point cloud or you do in the future, whatever. Then you get position and orientation. What is map? After we have this transformation matrix, we're trying to do a map. We're trying to generate a map at the local body, the local frame. This big M and local frame here. So this P here is our real-time point cloud. And the coordinate of body frame at epoch t, bt over here. With the odometry, we calculate this transformation matrix. We translate from bt back to t-1, and all the way trace back, as you got odometry, right, from time epoch to current epoch, all the way transfer back to the time 0 epoch over here. Then, if you have the leverage on or calibrations, you can make this back to the location, local frame. Then you have your point cloud at the location frame. This K here is the case point. T is the time T. And after you put all the P together, from first K to endpoint, you have your map. This is how you generate a map. Okay, this is how you generate. Pretty simple. And if you wish to use this map to help your odometry, you just do the scan to map, feedback there, you'll get a better position result. This is basically just how SLAM work. Looks pretty simple. But what's the problem? After you do understand, you got very fancy figure like this, and everyone love it. Like, oh, I do wonderful stuff. Yeah, but this is pretty simple stuff. Like, people do SLAM because they want to do localization and mapping at the same time. In the other word, that application is to go into somewhere I don't know. I go into unsurveyed areas, so we're using SLAM. Very typical example, Mars, we do that. But now people talking about using SLAM, autonomous driving. You put it to San Francisco. So this is very different, right? So the environment, is it unknown environment? Would you enjoy driving to San Francisco without any experiences at the first time? Not really like it, right? And what is different? This is unsurveyed environment going super slow. And that environment usually pretty static, right? Pretty static. It's not coming with a lot of different animals here, right? So that makes a lot of assumption violations when we want to put the algorithm developed for this into the application using this. What is that? The first violation is the phase dynamics. So we talk about the principle of LiDAR. You have 32 channels vertically, and you have to turn 360 degrees, right? So usually LiDAR gives you 5 to 20 hertz update rate. In the other word, in these circles, it's 5 to 20. You have to finish within 0.2 seconds or 0.5 seconds. This is what you have to finish. So you have to do a scan. Supposedly, if you are turning, you are making a turn, and this is where you started, the LiDAR starting to scan, going to make a circle, and you turn really fast, like what you see in the previous video. Then when you turn to this point, it's 360 degrees. But your orientation and location change. That will make your LiDAR scan is actually looking like the dashed line over here. So you have to consider this because it was going really slow, but it's okay. But now when we go into urban environment, sometimes when you turn it's pretty fast. So that makes problems. So if we didn't do anything about this, just directly using this dashed line point cloud, you do slant, you will see this is supposed to be the same line, but there's offset over there. But as a navigation researcher, we know that we have a lot of good stuff. One of that is inertial measurement unit. You have gyroscope, you have accelerometer, it's up there, it's super fast, you can do 1,000 hertz per second. After you have that, you consider that and put it into conversation, you can have this. So this is not hard. This can be easily be dealt with. After applying this acceleration and rotation, consider it and put it into model. Because in each of the channel, we know the time, so we can compensate back. Okay, so that's what we do. It's easy. But the second one is more tricky. Is dynamic objects. In San Francisco, there are a lot of cars around you, right? So what does it affect to our LiDAR? So for example, in this case, we have a point cloud, three points. We have this point 1, point 2, point 3. Okay, so this is our location at previous epoch t-1 when we go into epoch t. So this change, because my transformation changed, so it also changed the distance between myself, my ego vehicle, to the different objects. So the dashed line changed to black line because of my movement. So I can infer my change by looking at the distance here. That's basically how it works. But when you have a dynamic objects, this change, this distance change from this to this is not only because of you, because the vehicle it moves itself. So that makes a problem. Because we were assuming that the object reflecting the distance is static. But when it's moving, it is a problem. I'll give you a crazy example. Like if you're stuck in the traffic and two side of you and front side of you are all buses, what do you LiDAR see? It's basically my distance to LiDAR, right? So if we all move in together with the bus, you see this is what traffic stuck like, right? So your distance comparing to the bus actually not changing at all. So looking at this odometry, you believe you're steady there, not moving. So that's the crazy part. So dynamic object need to be handled for slant. Okay, so I'm just saying a typical example that we have in Hong Kong. You have a lot of car around you, and Hong Kong we have double deck bus. It's colonized by the UK, so we have this kind of stuff. Very big vehicles make you blind, make your LiDAR blind. We have this a lot. So we have to deal with this. So we want to put this autonomous driving into urban. We need to look at its performance. So starting from 2018, we're looking at, okay, let's pick a popular LiDAR slant that the open source code is available. We test in urban, see how it goes. We have a sparse, suburban, and urban. We test in dense traffic and normal traffic example, and this is a slant. So basically, we usually run like an open loop, which is you don't come in back, you don't use closed loop detection. You're just going a loop like 1 kilometer stuff, and you're going to see your starting point all the way to endpoint, how much it changed. Okay, this means the arrow here, the endpoint here is the y-axis over here. And we're going to also to quantify the traffic by how many cars around me and calculate the mean and normalize it into the traffic conditions here. So this is in sparse areas. In x-axis, you see like normal traffic to dense traffic. And this is the 2D arrow. This is the relative arrow. You can see whenever you are in sparse, whenever you are in urban, whenever you are in dense urban, crazy 25 meters. So traffic do matter to this slant. So we only confirm traffic matters then. We haven't considered how to deal with that. This is what we found. Okay, after that, we're going to look at, okay, so since we're doing GPS for a long time and want to do LiDAR for the first time, so we're going to looking at in the existing open source code. So existing open source code, there are a lot of good papers talking about LiDAR, but all the papers you see over here are existing open source code. You can download, you run, you do the bash, you put a command, and you can do position. And we classify it into point-wise and feature-wise, and we compare the performance and looking at the math with the differences. But in this talk today, we only want to talk about 3: ICP, NDT, and law. If you try to approach LiDAR slant, this is the 3 approach people use the most. So let's look at the 3. Okay. So what is ICP? ICP is simple. Like what we taught you, that we have a 2-point cloud, which is trying to match the distance between the point using changing of the RMT, make it match. Pretty simple. How many points I use? You can down filtering a little bit by basically looking at the point. And the next one is called NDT, which is normal distribution transform. So basically, when you have a lot of point clouds, you vexelize it. You put all the point inside one vexel. You can make it like a 2 meter, 2 meter per meter grid, and you calculate all the point there and trying to match the point, trying to model the point as a normal distribution. So in the end, you gotta have so many normal distributions in all the grid. Over here, you have so many different normal distributions. Then you try in your map or in your previous scan, you also have the points. So you have a lot of normal distribution here. What you do, you want to find an RT change in this one, match back, make it the maximum likelihood. So this is a NDT. The third one,
you scan in vertical too?
You scan vertical and also horizontally, 360 degrees.
So you get altitude also.
Yes, but it's a very limited. It's only 40 degrees comparing to 360 degrees. And yeah. So like for the feature base, because this is still a lot of point you have to take consideration. People want to make it faster. So when you see like we have a point cloud, I have an object. Let's say this is an object. Then I only looking at the plane feature and the edge, which is the connection of two lines. I using plane and edge only as the distinctive features, and I only match this plane and edge, which is not using all the points. I'm just trying to do feature detection, which is similar to visual geometry. So the feature detection, after I have the features, I match the feature on edge and the plane, edge and the plane. So this is the three most popular methods in LiDAR scan industry. Basically, you can see like I will tell you which one is the best for urban. So we do an experiment. We have this car. So in this car, we have a 216 channel and 132 channel and all the stuff. We have a no RTL band with inertial explorer and ground truth. We have the articulate system and ground truth. And we're testing in two different scenarios. This is suburban scenario, pretty rare in Hong Kong, but similar to what we have here. Yeah. And this is what we have usually every day. Hong Kong urban, you have all the cars and all the buildings, that's crazy. And we test this one. If you're interested in all this data set, we have the data set published as UrbanNet. It's basically a GitHub page. You just go GitHub and download all the stuff. If you have any questions, mail me. We can help you to make everything work. We even have the video to tell you how to run LiDAR NDT, whatever stuff. Yeah, we're trying to advocate people to work in this field from GNSS. Yes, so we do the accuracy and efficiency evaluations. Data one, suburban, less traffic, less features. Data two, urban Kenya, heavy traffic, more features. This is the trajectory. And it's a three method we compare. And in here, we talk about relative translation errors here. So this is between 2 seconds, between 2 seconds, between, like 1 second change. So this is the performance that we get. 0.3 from long, 0.4 from long in this data set one, so much better than the others. In rotation, they are performed quite similar. But what is good for long is that the computational cost. You can see in the y-axis, the orange color over here, the low. Computational low is super low. So lightweighted, so people love it. It is lightweighted because if they were using a lot of point, right? But you also trace only the features and match only those features. Okay. So eventually we select long as a basis to develop our LiDAR lens because we want to do for our own laboratory for our own test later. So we choose long. So long is open source code. It's developed by Dr. Zhang Ji from CMU. So we basically just get the code and collect data, very difficult data, by the way, and testing in this environment. This is about 3 kilometers. And the color here means different altitude, different height. Okay. So you can see we're starting from here, driving all the way back. You see a significant drift in z-axis. And that is pretty straightforward. They have only 40 degrees here, minus 30, up 10, and 360 degree horizontal. So obviously their constraint in vertical axis is much weaker. Similar to our GNSS, right? We have only 90 degree above, and the minus 90 we don't have. But this one, we have only 40 degree. So they were drift. So we saw this problem, and what can we do? Simply, we try to say, okay, what can we provide more information to this vertical plane? The ground. Usually the car driving on the ground, right? So usually, I'm talking about usually, there's still cases, right? So driving on the ground. So if we can use the floor detections as one more constraint, additional constraint, which is giving my model that particular directions. If we can do that, the performance will be better. So the idea basically is just super simple. This part is a transitional long. We just add the ground plane detection here, and also of course we're using those closure detections, and everything optimized by vector graph. Boom, and that's the result. So the cons is we solve the problem position drifting in the axis, which is the vertical axis. The cons is we make assumptions. The vehicle only driving on the flat plane. Because when I published this paper in navigation, those guys asking me, how about this slope? How about you coming to this kind of areas, mountains area? I know it doesn't work. But in Hong Kong, we have relatively flat. So I said this is for Hong Kong. After we have this, the performance is actually, I think it's pretty amazing. Let's take a look. So this is about 4 meters. And you see like this area is like in New York Fifth Avenue. This is called Mongkok in Hong Kong. This is crazy being urban. A lot of cars, a lot of buses over there. So we're trying to do that. And the performance is, it doesn't work, but it's okay. Basically just the same one. So you can see like this is the map we come out eventually. Again, the color here, the color here is the height. So you can see we make it in the same height. And if we're using loose closure coming back to the point, that point coming back to the same point, the difference is only 30 centimeters. So we believe, oh, this is a good slant, at least for this environment, So after we have this, oh, you can take a look. This is another proof to see this is really good. You can see this line. We can clearly see this line by using this technology. So if we can see this all consistent, you can do pattern recognitions to get what is building, what is line, and that stuff much easier. So this is we are very excited about this, and we end up collaborate with UC Berkeley. I work with Professor Tomisuka and Dr. Zhang. This one, I'm not sure if it works. Let me try again. Really want to show off. Okay, not for this time. Yeah, so in the end, we come up with this one. We are working with this point cloud, and they are working with these map instructions using cameras and LiDAR, and we put it together as a team. So what I want to say about this HD map, high definition map, is that they have so many different vector layers. They have a landmarking, traffic pole, whatever, high confidence route, etc. But they have a point cloud here. Why they have a point cloud here? That is very essential for your localizations. Why it is essential for your localization? So we are coming to a war from LiDAR split to LiDAR matching, as I call it, LiDAR matching. So we have a real-time point cloud match the point cloud in the HD map. So in this same flow, the model here become like the point cloud that pre-built in the HD map. So in the previous one, this is called initial scan, but now this one is changed with a pre-built PCD map. And the same equation, this was the previous scan, now become your point cloud map in the map. Now your RT now is this T is not BT to BT minus 1. Now it's BT to the local frame, which is your map coordinate. That's the differences. So after we have this LiDAR matching, which I believe the most of the current autonomous driving are using this one. I hope it is. I think it is. Then what's the problem of this one? Let's look at, okay, we talk about dynamic objects, a big problem for SLAM, right? So how about it is for LiDAR matching? So we're trying to do one simulation. So we have the real data collected at point cloud. Then we do a simulation of what? We simulate there are bounding boxes like buses or car, like here. After we simulate it, that we make, we made a point cloud like occlude. So you cannot see those point cloud anymore. So we're trying to make this point cloud only to this distance, only to this distance. It doesn't really go into where the map is. So after we do this, we're going to test 1-2 scenario, low occlusion and high occlusions. So these are because we do Monte Carlo. So you see like in the maximum 70% of the point being excluded, occluded. 70% of the point being occluded. Your maximum error in 3D in this particular case is 42 centimeters. 70%. This is your point cloud. When you look like that, I still give you 72 centimeters. So after we see the simulations, I told my student we should stop working as SLAM. This is a soft problem. 70% of the point cloud are occluded. You still got 42 centimeters. That's why people don't need SLAM algorithm anymore. They just use the map and just using the matching. I hope I'm right, yeah. So dynamic matching is not so much a problem anymore for my personal perspective. So after we see this, I was like, is this the end of the world? So we believe that the LiDAR matching is very satisfactory, but can we just rely on LiDAR matching for safety critical application? I shouldn't explain too much in this GPS lab because everyone knows that this is very important. So you have accuracy, it's good in one hand, but we need integrity monitoring. I know I exaggerate this a little bit, but the point is, if you want to rely on something, we need to do integrity monitoring. Okay, for example, in our LiDAR matching localizations, most of the time it's like this. You have a learn limit, like the maximum tolerable error, usually like 25 centimeter, most of the time. But sometimes something just go wrong, right? Like in this particular simulation cases, when you're doing turning, that error, if we exaggerate the noise as well, it can go to 1 meter in turning. But in most of the case, it is okay. In most of the case, it is okay. But sometimes something just go wrong. So we have to do something about this. And that's why I'm here, trying to learn from all of you and to explain how my first approach on doing that, which is similar to classical GPS example. So like I'm going to talk about this, what you're very familiar. Bear with me for 2 minutes. So we're learning from experience in GNSS and aviations. We want to make our integrity risk smaller than a given one. So you want to make your estimate positions that comparing to true position, that arrow, they're larger than a limit, but you don't alert. This probability is smaller than the risk. This is how we do integrity monitoring. So this alert limit, like I said, in auto driving, I believe it's around 20 to 25 centimeter. They didn't publish a document officially, but that's the number because the tie is around that width. Okay, so and that integrity risk is like what's your liability there, right? So this is simple, but the problem is how do you get this error, right? How do you in the real time you don't have error? So what we can do is to calculate the position level, which is as a regard as the maximum positioning error that we could have under a certain statistical behavior. So after that, the integrity monitoring it should be like this. The error is larger than alert limit, and if my position level also set is smaller than alert limit, but it is not, then that's the risk that we have. Basically, the same as civil aviation. Then what can we do from this all the way to LiDAR? So starting from fault detection and exclusions, we need an outlier-free measurements. We need a convex model. Then we can do position level calculations for integrity monitoring. Then comparing to GNSS LiDAR, first challenges. GNSS, you have a GPS, you have about 10, 12, 15. GNSS, you can 30, 40, but LiDAR, you have 10,000. You have 10,000 measurements, even more than that, depending on how you use it. So if you want to do FDE, whatever approach you use, grid approach, solution separations, the calculation is going to be crazy. So what we want to do is we gotta have a method to select. We're gonna have a method to select the feature. So how do we find the best feature? In GNSS term, we're going to find those satellites who contribute the most and using only them. That's what we want to do. I will talk about the detail of this stuff. Then the second one is convex property. So GNSS, because satellite is so far away, almost it's definitely linear, so its convexity is very easily verified. But for a LiDAR approach, your initial guess is super important. If you, let's say, if you guess that you're in Taiwan using the Taiwan initial point, and to compare with the map in San Francisco, it doesn't work. So you gotta have a bunch of initial guesses that is closing to your location, and see if you can find that initial guesses can give you a convex solutions. So we want to verify that. We want to verify that so that we give a certain range of initial guess. We can believe that the solution is convex. You can find a local minima, but that local minima is absolutely minima. But that one's hard. We can talk about that. Okay, so we're trying to do that. How to certify that? The third one is do a PO calculation. A lot of researchers also try to calculate the position level. But what we try is we're also trying to protect the rotation as well. We don't want to look at the translation, but also look at the rotations. And I will tell you how we do it. Okay, that's the framework of the day. How much time I already spent? Have now. Good time. Yeah. Okay. So look at the proposed framework. We have a point cloud, we have a map. That's what we given. This is a LiDAR matching approach. We have a cloud, we have a map. Then the first thing we want to do feature selection. How do we do that? As a typical long, so you have a feature extraction. We get a plane here only for simplicity. We have a planary feature, Then you do point-plane association, talk about it later. Then you do this information matrix analysis, very similar to our DAP, just in an inverse way. And after we have this information matrix, we look at the eigenvalue to find a minimal eigenvalue. If this passes the certain threshold, then we select that. And after that, we put those features into nonlinear optimization. Then we're going to check the convexity of it. If it is convex, then we can do FDE. In the FDE, we put it into priority space because that we want our bias independent with the state somehow. So we calculate the priority space. Then do chi-square for detect for exclusion until the chi-square test pass. After the chi-square test pass, we can calculate rotations, rotation level. We can calculate translation rotation level. This is the overall flow. So let's talk about one by one. We do planary feature-based LiDAR localizations, which means we're trying to find the pose of the different time inside the map coordinate. So this is the transformation matrix from your K epoch comparing to the map coordinate. You have the rotation and translations in Euclidean space, and your rotation this is in your Lie group space. Translation is in real value space. So for the initial guess, we apply uniform motion assumptions. Then let's talk about the model itself. How do we do the point-to-plane associations? This purple color here is the measurement, the real-time PCB measurement that we have. T over here is the state we're trying to estimate. But in here, we given here as an initial guess. After you have a measurement, you have an initial guess of transformation matches. Then you put your point cloud based on the initial guess to the map coordinate, which is the red dot over here, the red dot over here. Then in your map, you have a lot of points in your map. You find the closest 5 points for each of the point and make it as a plane. And make it as using 5 points to make it as a plane. You can find a plane to contain the 5 points. After you have the plane, this point to this plane distance is calculated as the normal vectors plus the distance. This is developed by Dr. Zhang Jing by himself, but this is quite important. So let me finish this one. So this is your distance from point to plane, calculated here as green, which is R over here. We call it as a residual functions here. R is a residual function that we have. So your objective functions, you're going to find a translation, you're going to find a transformation matrix, then make your cos minimized. That cos is a function of your state. And that state can be calculated as the distance of each of the feature K, each of feature K. So time K and feature I calculate weighted averagely, the error. So this is how you calculate your transformation matrix. Do we have a question here? It's pretty okay, right? Cool. Yes. But this is our objection functions. Then, because we have more than just one feature, right? So we selecting n feature, for example, select n features here. Then your cost function, we want to make this t as a state space that we usually see x. So we want to make it as matrix. So this is the post-state notations, which is what we have, transformation matrix R and T. We want to make it as something like this: x rotation and translation. One vector 6 by 1. Because we already calculate the residual functions here R. So the residual function is actually equals to a lot of different stuff. But you do Jacobian, you can calculate it. You can do the Jacobian and the state x plus the normal noise here. The Jacobian basically is these Rx functions. This RK function. This RK function is the previous page. We talked about the distance, the point to distance range. After you have that, you divide it, the partial differential by the state. Then you get your Jacobian. Okay, you got your Jacobian. Then this is we're assuming it's Gaussian noise for the time being. Then we're assuming that the noise are uncorrelated for the time being because we don't know how to do if they are correlated. so we're assuming they are uncorrelated. We're assuming it's Gaussian because we don't know how to do it if it's not Gaussian. Talk about it in the future where we can think about how. And this is your covariance matrix, which is your weighting matrix, the inverse of covariance matrix. Weighting is actually just the standard deviation noises of your measurement. Okay, of your measurement. Measurements are here. Okay, so this is to this point, it looks a bit similar to our GNSS, isn't it? You have the state, you have the measurements, you have the model J. So this is what we're trying to make it look like, so that we can start and learn from the giant to do integrity monitoring, and this is how we do it. Before I talk about the FDE, we talk about that there are so many features. So we want to make feature selections to make it computational acceptable. For example, we have so many laser beams, but eventually our goal is to make it like only a few, which is representative. Okay, but how to do it mathematically? How to do it elegantly? That's the questions. So in fact, by each of the features I, we can calculate the information matrix. The information matrix is your measurement noise with your measurement model as a Jacobian in this context. The Jacobian transport multiplied by weightings, multiplied by Jacobian. This is information matrix. Yes. And after you have this information matrix, this one, I actually don't know how to say this notation. Gamma? Yeah. Is it gamma? Yeah. Gamma. Yes. So after you have this gamma here, what we do is that you get this gamma, you do the eigendecompositions, which is trying to find in this information, are we trying to find the assets that can represent the model the most? Okay. If you look at the eigenvalue, that means in this direction, how many information, how many power you have to constrain it. So we do the eigenvalue. If the eigenvalue is big, for those who is not familiar with this eigenvalue stuff, you can regard it as the inverse of that. It's not very accurate, but for you to understand, it's the inverse of that. Okay. So when you have this eigenvalue, when it's big, it's the rich information. When it's small, it's little information. So this is basically what we do. We're trying to play with this information matrix. We're trying to do eigendecomposition to find out the good one, the good eye measurement model. Okay. So this is how it goes. We have all the features in the current scan. Okay. We have all the features in the current scan. And as proven by this paper, Dr. Zhao, that this LiDAR feature is actually a cardinality restrictions, meaning that when you have enough number of measurements, your performance is not going to improve anymore. Okay, so they prove that, and we also see that in our data. So if we make this n is the number of the features we're going to choose, then we're going to firstly randomly select a bunch of subsets from what we have in the current scan. After that, we calculate information one by one. Okay, information is one by one to see which is a good one, is a bad one. And after you have the information matrix, you can actually use that information matrix and also use the measurement to calculate the measurement model that you have for the subset. Then in those eigenvalues you find, you're looking at the minimum one. Because the minimum one is in some of the directions you cannot constrain. Then your solution won't be too good. Okay? If you find you find I measurement that give you the maxima of the minimum eigenvalue, the maximum of the minimum eigenvalue, then that is a good measurement. That is a good step line in a sense. That is a good step line. And after that, you put it into the feature set that you have. And if it is smaller than this one, then it's good. Then if it is smaller than this one, it's smaller than this one, then we should choose all the way to this point and until it's good enough. Okay, this is what we do for the selections. Okay. Then for FDE, I also need to talk a little bit about FDE. I hope the math is okay. This is 1 o'clock in the afternoon. I hope I can make you excited. So the residual factors here are we have. Now looking at this, we will talk about this parity space. When we have the 40 measurements, then you have the bias over here, decay over here, compared to the previous one. Okay. So now let's see how we're supposed to deal with that. So what we do is we're using a projection matrix U. We call it that projection matrix U. Bring your residual into a parity space. That means your U modified by the Jacobian matrix, which is your model, that equals to 0. So if you can find a matrix that modified by Jacobian equals to 0, what it can bring you, what it can bring you is that you put this UK over here. Then UK modified by JK, this part is already 0. So basically, you are in a space with bias and noises only. You are in a space with bias and noises. How to derive this UK? There's a 2 Korean paper talking about it. We're just directly using the conclusion here. So this is the UK, the projection matrix over here. If you put it there, then your residual parity space is only with bias and noises in parity space. After that, depending on you have a 40 measurement, then your UK should be 0. And if you have 40 measurement, that will be large. Then just do a typical chi-square test. A typical chi-square test. You will do. Okay. So what we do is like the isolation from the state enhance the measurement model, the sensitivity of measure model on the detection of the fault. Right. So after we have that, the whole iterative FD is looking like this. We have the represented features. After we have the features, we do normalization. We got the model. After we have model, we have the residual. We put the residual in the parity space. In the parity space, we do chi-square test. After we do the chi-square test, if it's smaller, if it's not smaller, then we just do exclusion. How we do exclusions? When you have the residual, you're normalizing with your noises. You find the one with the largest residual and exclude it and put it back until it is good. So as I said, I'm translating classical GNSS monitoring here. Okay, then you have no faulty measurements here. Now let's look at how we calculate the PL quantifications. We basically follow the paper of RAM with multiple faults. If you're familiar with Angus' work in 2006, okay, so we follow that work. So in that PL formulation, we have this maximum error caused by bias, maximum error caused by noises. Let's look at the bias one, which is the bias means like the outlier failed to be excluded. If you this is my credential. It's important stuff, yeah. So we follow the method of the RAM with multiple faults and use it for parity space. So basically, when you have a bias, this is the error it's going to bring you, right? This is the model part. This is noise covariance. This is the model part, similar to our GNSS, HS, and covariance, right? So after you have this one, we're trying to separate translation and rotations. By doing that, we give a selections matrix, which is we call it a adapter matrix. I'm not sure which is the good term to use, which is looking at which component of the state, which component of the pose you want to see. For example, you can look at translation by selecting 111 here, rotation 111 here, or you only looking on the axis, just choose one. So that's what we call a adapter matrix. So basically, this is pretty simple. You just put all this here, here, here. You've got a noise covariance of your state here, according to your state C. After your state C, then basically what we choose here is to find a maxima slope multiplied by the chi-square threshold. The maxima slope according to a certain measurement K. So for example, if we're choosing only, this is called binary vector. I'm not sure the term as well. So you're just choosing the measurement you want to look at and finding out load all of the K to make your slope the biggest, the biggest. Then you multiply by the chi-square threshold, then it give you this term over here. So this term is very important because it's part of the bias caused by the partition, the maximum error caused by the bias that failed to be excluded. So if you look at here, you can calculate the bias for Tx, translation x, y, z, rotation x, y, z by using that equations here. Okay, the time is getting there, so I'm going to speed up a little bit. And for noises, it's pretty simple. You have to miss detections and calculate the noises. This is a very typical stuff. So after this one, we can calculate the partition level. Let's look at some result finally. So we look at the absolute translation error, absolute rotation error. That calibration is bring by GNSS RTK. I make it into absolute format, coordinate. So we can do ATE and RTE. So in PLO, we compare conventional 3 sigma method and also develop the PLO method and the same environment that we test. Okay, here's the accuracy. So we talk about intelligent. We talk about feature selections. So we only select 20% of the point. When you see 20% of the point here, y-axis is the error, right? So 6%, it was 27 centimeter, 18 centimeter, all the way to 15 centimeter. As you go more, it doesn't really give you more. So 20% is that what we decide. Okay, so rotation, you got exactly the same stuff. This is translation, this is rotation, you got exactly the same stuff. So if you look at the arrows, when this scenario 1, you have this 1 and 2 scenario over here. Then if you select only 6%, it still give you those high peak. But when your percentage is going up, then it give you pretty decent positioning error. For rotation as well, it give you a very decent degree. Especially only when you're doing rotations, go to about 1 degree. But 1 degree, I think is okay. It's okay, yeah. So this is finally the PL comparison. So the green one here is the positioning error. The blue one is the 3 sigma. Because in auto driving, they're using sigma, 3 sigma to bounce stuff. So that's why we compare the benchmark with them. And PL is the one we learn from GNSS and put it into LiDAR mentioned. So you can see this is roughly how it looked like. And if you look at the percentage, the PL is actually larger than AP, which is the bounded error. This is about 87, 78, 99 in SSs. And for conventional, that is not so much to be mentioned. Yeah. The fault detection, the false alarm, we do 95%, this decision we do 99%. And for the measurement noise, here, we select 6 centimeter. We select 6 centimeter because that's also indicated by the manufacturers, but which we try a different value, but you still see the trend over here. The partition level is looking like this. So this is what we get. After we have this, we need to say, okay, this partition level, is it trustworthy? So we talk about the convexity stuff. How do we verify its convexity? Okay, so this is our absorption functions. So we're trying to minimize these absorption functions here. So we're trying to find a minima, meaning like we're trying to find a minima value instead of a maximum, instead of a zero point, we're trying to find a minima value. This is wonderful figure, isn't it? Coming from math is fun. Fun, yeah. So we're trying to find a minima value. So in minima value, whatever you want to find minima, you want to find zero point, you want to find local point, definitely make it Jacobian is 0, right? This is everyone knows. So how about Hessian? Hessian is the partial differential of the state to the Jacobian, right? So which is this one. This is Jacobian, your cos functions, right? Partial differential by the state, then do it twice, you get Hessian. So when you have these Hessians, if your Hessian matrix tell you that it is larger than 0, then it means you can find local minima around the initial guess that you give. Around the initial guess that you give. And in this part, you give in here, it can come to the minima issue. Okay? So we have a derivation about this one. It's pretty complicated. I don't want to bring too much. But after you can calculate this Hessian matrix, what we do is, in this Hessian matrix, we also do eigenvalue decomposition, again, to find the minima eigen. So that if the minima eigen is larger than 0, we are certain we find local minima means it's strictly convex. That's what we do. We calculate this H matrix based on our derivations, then calculate the minimized eigenvalue. If that is also larger than 0, we said we have a convex solutions here. Okay. So because we can only find local minima in this initial guess system, so we give a different pulse initial guess. We give like okay, for example, 5 meter in translations in x-axis, y-axis, z-axis, or all the axes, or give an initial error with 10 degrees. We give a different initial error, which we believe is pretty exaggerated in terms of a uniform motion initial guess assumptions. So this is the result. You see, this y-axis is the minima eigenvalue of the Hessian matrix. So you can see that even in this part, it is still larger than 0. The slope is not pretty, but still larger than 0. Meaning like in this part, your solutions, all the parts, your solution is convex. So we already verify that. Okay. Then with that, I can show you some of the result. You see, like if we give an initial guess, 5 meter offset, solution 1 5 meter offset, initial guess, when it converge, it's good. When you give a 10 degree offset, the initial direction, forward direction, converge, it's good. And we look at the cos functions, different state space. This is ty to tx, tz to tx, tz to ty. Whatever you see, you can find the minimum value. The cos, you can find the minimum value. In here, the color looks the same, but it's actually just because of the degrees, 90, 100 something to 0. But still, it is convex. So we have the same result for can I quickly go to? We have 20%. Choose 20%. Your ATE doesn't go below too much. Your ARE also. And then we give an even crazier initial guess. 30 meters, 3 meters, given sometimes 30 degrees in the beginning, and see how it goes. You still get the same minimized eigenvalue larger than 0, the convex, and your solution can still converge. Your solution can still converge. Okay, and let's look at the PL quantifications of this case. It's actually surprisingly it's getting better compared to the previous one. We get about like the worst one is 85%, which we are pretty happy about it. So this is the result we have at this moment. We have a lot of problems to be solved. We'll discuss that together with you. So the conclusion here is we're doing LiDAR slang in challenging environment. It's challenging the environment, and with a given priori map, LiDAR matching can be satisfactory in terms of accuracy in most of the time. And we developed this safety-aware LiDAR matching, which is doing the feature selections, doing the FDE, and calculating the position level and verifying its convexity. That's what we do. But are we doing LiDAR localization with integrity? Of course not yet. This is very far. This is just a first try and first benchmark to see what can we do by leveraging the knowledge from GNSS. So I talked about this. What we do is step 1 and step 2, FDE and PL. But actually, there's a lot of things to be done. Then step 0, you need to identify what is the error noises. You need to know how to model each of the noises. You need to provide correction to that. And you need to define a nominal noise model as well. Otherwise, it's impossible. So by doing all of that, you can do this FDE, but that's a lot of work. For example, what could be the error source? That your real-time PCB is not existing in the PCB map with dynamic object, or the tree just changed. It was a lot of leaves, but in winter it's no leaf. That's one point. Or your real-time PCB is affected by fog or affected by rain. That make distance change as well. Or your offline PCB just not update enough. Some building just disappeared, but you still put it there. That's all error sources we could have. So my team is thinking like, oh, we could model all this. It's a lot of work. So we are thinking, can we strictly talk about how to use in GMM to solve that? So that will be my next journey, to looking at how to put in GMM in all of this and trying to leverage that. Thank you. Is that too long?
No, it's good.
Excuse me, yeah.
Any questions?
I'm talking too much, too fast.
I have lots of questions.
It's not exactly what you presented, but you think Elon Musk is correct that Tesla can do this without LiDAR?
This is recorded? No, I don't think we can do that. I don't think we can do that because in the visual one, like the integrity is even harder to find. LiDAR is a clear measurements, but visuals in terms of the depth. How do you calculate? Especially they talk about end-to-end model to do the visual odometry. How do you verify this network? We don't know the math. We don't understand it. How can we bound the error? So I feel it's very, very, very hard.
So what is the key measurement that you have with LiDAR that he does not have with his camera and his radar?
The absolute measures. Because what LiDAR they're doing the visual odometry, which is like using the two change to recover the depth. Or you're using like two stereo camera, using this one to calculate it. But that one, the accuracy goes down when the distance goes far. So, but LiDAR is absolute, it's very clear, it's just time of flight. That's noise model is much clearer.
So it's a fundamental difference.
I think so. I think so. So I believe in LiDAR do L4. I believe in Vision one to do L2.5, L3, which is liabilities or human beings.
Yeah. All these cars we see with this thing spinning, is that the LiDAR?
Yes. It's move out its eyes, right?
Radar blurs it too much. Radar is a problem. You can get accurate distances, but it's kind of it's not a point measurement. It's kind of a surface measurement.
Exactly. So what they do, they currently when they install the LiDAR, they consider how to cover the best. So what I say, just one and doing like this, right? So you see a LiDAR looking like this, some LiDAR looking like that. They're trying to cover even wider of the elevation angle, trying to get more directions of measurements, make your model better. But yeah, but still, this integrity is still hard. As I said, there's so many problems. You don't know the map is good, whatever. Yeah, still very hard.
I'll turn off my recorder.
Hi, colleagues in other views.
Yeah.
Well, you take a drive in a Waymo car and then drive in a Tesla and compare the performance and the visuals that they're showing you, like, yeah, it's not close. All right.
Yeah, you can't. You're comparing apples and oranges to say, like, just the level of integrity on Tesla, like I said, is more like L2, L2.5.
Yeah. Take your own responsibility. We're just trying to help you.
And you work for Waymo, right?
Yeah.
No bias there. No bias. No bias.
No bias, just kidding.
So
Thank you,
question with the convexity part. So here we're only really concerned with the local convexity of the cost function, right? And the claim is that in real time, you check the Hessian at the optimal position, and then you choose some samples around to ensure that it's actually retaining the convexity nearby,
Yes.
right?
Yes. Yes.
But so I guess the question is, we still have no idea how the cost function looks on a global sense,
Yes.
right? So is the idea that you're still sort of tracking this over time, and because you're maintaining the convexity over time, that you're more certain that you're actually going to converge?
That's correct.
Okay.
But more importantly, we want to give a specification on how good of the initial guess you should give. So we can still give it convexity. Because in this system, there's no absolute minimum, local minimum. There's no absolute minimum, global minimum. There's no something like that. Because your model looking by city, how can you just get a point? This is not GNSS, this is not like that. So there's only local minimum. But how much initial guess, how wide of initial guess you can cover, that is within the model you build for your LiDAR metric. Planar, age, NDT, they all look different. But in the map, you're going to extract that the same and also give a different initial requirement by different model that you use. That's the idea here.
But based on what you're saying, are you taking out all the dynamic, what you think are dynamic points? Because if you're for just the map, if there were no cars, no moving objects, I would agree with your convexity assumption, but
Exactly. So that's why we need the fault detection and exclusion. Currently, we're still assuming like very naive games. We're just trying to leverage classical one. We just assume one at a time, but this is definitely not the case. So we believe that there are multiple faults. And how do you dealing with multiple fault? You do greedy. If you do global search, that's crazy computational. You don't do that. You do greedy, then you could have a problem that one is very easy. Yeah. So what our idea is to looking at the GMN, how to consider there are multiple ones. Yeah.
Your HD maps don't even remove your dynamic points, right? Those are all generated by war driving, but driving around and making measurements anyways.
Right. They're
But then people go through them and
they clean up. Yeah. So they're
manually using the bugs.
it's a lot.
Huh?
How many features were you using
In this case?
in the FDE?
In the FDE, in this case, we're using around 200. We're using 200 only. Yeah.
And let's say if you had a car there, how many features would that be?
Is it if there's a car here?
Yeah.
If you're selecting like the strategy that we have, the sparse enough, I think basically 1 or 2, because we're trying to find a point and fit the plane, right? Trying to find a point and fit the plane and trying to calculate distance. So if your selection is geometrically sparse enough, that should only come to 1 or 2. Yeah.
So that should help you define what your failure modes would be. If those are the ones that you are worried about.
Yes.
Moving parts. You would start thinking about how to group those faults, right? And
Exactly.
see how to restrict and not to have to do a global search, or also limit how many of those features are actually moving. I think there's things that you can do. And the fact that there are multiple faults, you limit that to maybe 5 or 6, it might be feasible.
Yeah, you're right, because if they are coming from the same vehicle, they are not independent. The W node is not independent. So I probably have to make it as 1 first. That's the first point. If they're coming from the same error sources. That's right. Thank you. That's important. Thank you. Yeah.
What do you think are this is gonna be a little bit long-winded question. What do you think are the kind of the big error sources that you need to kind of work on and understand better? When I look at your results with like your bounds, say, well, I'm getting about 90% of protecting overbounding the error. In aviation, we think, well, that's really bad, especially since you actually set a level of PMD of 1%. And you're like, well, that is like an order of magnitude over what I expect. And when in aviation, I try to protect at least an order of magnitude under what I expect.
Mm-hmm.
And so that naturally speaks, not necessarily that the model might be wrong, or method might be wrong, but maybe it's really, and you can see that, right, that the error models have to be better to make it all work.
Yes.
So what do you think are kind of the big challenges there?
Yes. In terms of the contribution of the error, I think it's a real-time measurements.
Okay.
Because it's just you have the dynamic object and all the stuff. But for me, I think the real-time measurement is the one to be excluded. So what we should look at is the map. Because like in this industry, the map is gold. People love the map. So if they can come up with a map to say, okay, I quantified my my performance of the map. I know how it looked like. I know how integrity-wise, what model you use, what the error should be. If I can have that, you got your map certified. And that is the infrastructures. everyone just using a map. So, and when I do FTE, I don't have to worry about the map that much. I just need to worry about my real-time measurement. I can make an assumption. Oh, my map is good to a certain level. So I will looking at the map first, then talk about how to dealing with those big ones.
So it goes back to what we're saying about the HD map. There's a lot of human involvement in it. And right now, even though it's cleaned up, we don't still have a quantification of how good that cleanup has been. Is that kind of what you're implying there?
Exactly.
Okay.
And also, if you want to make it automatically, then just using Slender, we can apply what we used over there, but the error just big. It's become not realistic.
And it means surveying. You have to survey your area before you go run autonomously.
Right.
So that's another huge cost.
Because what I gather now, they just drive it, they just war drive it, but
You drive it with a person behind the wheel.
Right.
As you're certifying your operational design domain, area in which you're operating.
that seems prone to a bit of error.
Yeah, but you're collecting so much data. It's sort of like your comment
So
about
how many times are you driving the same road over and over?
Yeah.
Yeah.
How many times?
lots.
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 I'm curious, I don't know enough about this.
But it's also interesting, like there are tricks that I've seen people play, like you mentioned about indoor GPS. So there's a company right now that is taking, every time you get an ad on your phone and it comes back, to certify that the ad was actually served to you, they record your phone, its number, location, and time.
Mhm.
And then they send it back. And if you remember, who's the gentleman? We had this one talk a long time ago where he shows this is not a pipe. And if you collect those data and you plot them, you can get a map of San Francisco.
Yeah.
Right? You can get a map indoors as well.
Yeah.
Where they're using your phone's recorded data in order to map all indoor spaces.
Okay.
Even though it's not accurate, like they just take humans and they look at the point clouds and they say, okay, I'm going to map these indoor points to this aisle in Kroger's or in Safeway. So they are getting down that, even though we all know that GPS doesn't work that well, they are cheating the system through just vast amounts of data. Yeah, just brute force data.
Yes. So they come.
Yeah, no, I mean, they can collect these data and in the absolute sense, these GPS points are bogus, but because they have a map, like Kroger's will give them a map of their indoors and someone will just by hand say, okay, these points belong to this aisle, these points belong to this aisle. And they can tell roughly where you are in the store over time.
So I believe the human being is reliable.
Yeah, but it's a ways of cheating on some of these things.
Yeah.
Like you said, you were using the ground plane in order to do it, but if you have the map, then you can do.
Yeah. If I have the terrain high, right? So we could terrain heights and I can probably use that. Yeah. Yes. Okay.
Great talk.
Go ahead.
Quick question on the inclusion of features and fault detection. Did you also look into some heuristic methods? Because if I remember correctly, Loam does a heuristic thing where if
Just 20%.
it picks a point in the middle and it says this is most probably an outlier because there's nothing next to it, so I'm just going to drop it.
Yes.
So is the feature inclusion after heuristic methods have already run, or do you not run heuristics?
Heuristic, you can also get a good performance. You can basically just do like every direction I just choose one. So you can still get a reasonable one. But what we're trying to do is trying to reduce the percentages at most. So we want to, because FTE, it matters. It matters. Yeah.
So just a quick follow-up to that. Do you think your performance will increase if you layer your method and do some heuristic fault detection before? Or do you think it will decrease because the heuristic is not very
We're
well
basically
quantified?
using heuristic as the initial point to filter out and then select the good one.
Okay.
Yes. That's a great question. You're working in this field, right?
Used to. Not anymore.
Yeah.
Any other questions?